We feel it every single day, right? The warmth from a cup of coffee, the chill on a winter morning. But what is heat really? I mean, on a fundamental level. Well, today we're going to find out. We're diving deep into the science that takes us from a simple shiver all the way to steam power.
It seems like such a basic question, but the answer is pretty mind-blowing, and it takes us right down to the world of atoms. So what is the real physical difference between a hot cup of coffee and a cold glass of water? Let's get into it.
Okay, so it all comes down to one thing: motion. See, everything around us is made of atoms and molecules that are constantly vibrating, just jiggling around. Hot simply means those atoms are moving and jiggling incredibly fast. And cold, well, that just means they're moving a whole lot slower. So temperature isn't really a thing in itself. It's just a measurement of how fast those atoms are moving.
To really get this, we're going to start with the absolute foundation, what heat and temperature actually are, and then look at the pretty clever ways we figured out how to measure all that jiggling.
You know the classic glass thermometer? It's a perfect example. As that red liquid inside gets warmer, its molecules start jiggling faster and faster, and they start to take up more space. They expand, and that expansion is what pushes the liquid up the little tube. It's such a simple, brilliant way to make that invisible molecular motion totally visible to us.
Now, we've got a few different scales to measure all this. You've got Celsius, which most of the world uses, where water freezes at a nice clean 0. Then there's Fahrenheit, common in the US, where water freezes at 32. But for scientists, the big one is Kelvin. And what's so cool about Kelvin is its starting point. Look at that bottom row, 0 Kelvin. That number represents a concept called absolute zero. And this is it. This is the theoretical floor for temperature, the ultimate cold. It's the point where those jiggling atoms and molecules slow down so much that they basically stop moving altogether. We've gotten incredibly close to it in labs, but it's this physical limit you can't quite reach. It's the point where there's literally no more heat energy left to remove.
So we know heat is atomic motion, but how does that motion get from the sun to your face, or from a hot stove burner into your dinner? Well, it turns out there are 3 main highways that heat energy uses to travel.
So our first highway is conduction. This is heat transfer through direct contact. Just imagine the atoms at the bottom of a metal pot on the stove. The flame makes them jiggle like crazy, and they start bumping into their neighbors, who bump into their neighbors, passing that energy all the way up the line. It's like a chain reaction. That's why a metal spoon left in a hot cup of tea gets hot so fast. Next up, we've got convection. Now, this happens in things that can flow, like liquids and gases. Think about a radiator in a room. The air right next to it gets warm, it expands, becomes less dense, and starts to rise. Then cooler, denser air sinks down to take its place, gets heated, and rises too. This whole process creates a constant circular flow, a convection current, that ends up warming the whole room. It's kind of like a tiny weather system right there in your house.
And our third and final highway is radiation. Now this one's the real rebel of the group, because unlike the other two, it doesn't need any stuff to travel through. It's pure energy moving as electromagnetic waves. This is how the sun's heat travels 93 million miles through the vacuum of space to reach us. It's the exact same type of heat you feel coming off a campfire or a hot grill. Okay, so we know heat makes things hotter. Simple enough. But what happens when you add a lot of heat? Well, that's when something way more dramatic happens. The very state of matter itself can transform. Let's look at the incredible power of these changing states.
Okay, picture this. We've got a 1 kilogram block of solid ice. It's sitting right at its melting point, 0 degrees Celsius. Our goal is to turn it into liquid water. But, and this is the key part, keep it at exactly 0 degrees Celsius. So how much energy do you think that takes?
It takes a surprisingly huge amount of what we call latent or hidden energy, 334 kilojoules. And none of that energy raises the temperature one bit. Its entire job is just to break the rigid bonds holding the water molecules in that solid ice crystal, letting them finally start to flow past each other as a liquid. But honestly, that's nothing compared to this next jump. Let's take that same kilogram of water, heat it all the way up to its boiling point of 100 degrees Celsius, and now we want to turn it into steam, again at that same 100-degree temperature. The energy needed for this is just staggering, 2,260 kilojoules. That is a massive amount of hidden energy.
And every single bit of it is going into breaking the last of the bonds between those water molecules, letting them finally fly apart as a gas.
So here's the crucial takeaway. Just look at the difference. It takes almost 7 times more energy to boil water into steam than it does to just melt ice. This immense energy stored in steam is why it can cause such bad burns, and it's the very same principle that literally powered the Industrial Revolution with steam engines.
So, we've got the foundation, we know how heat moves, and we've seen how it can transform matter. So now let's look at how we've taken these fundamental rules and used them to build the modern world around us.
We really only control heat in 2 main ways. First, we use insulators, like a wool sweater or the fluffy fiberglass in your walls. They work by trapping tiny pockets of air to slow down conduction and convection. And second, we use reflectors. Think of the shiny inside of a thermos or those emergency space blankets. They literally bounce heat radiation away. It's all just clever ways of messing with those 3 highways of heat we talked about.
So what about making things cold? Well, a refrigerator doesn't actually make cold. It's really just a heat pump. It uses a special fluid and forces it to evaporate inside the fridge. And just like when water boils, that phase change sucks up a ton of latent heat, which makes the inside of the fridge cold. Then it just pumps that heat to the coils on the back and releases it into your kitchen. It's phase change in a box.
But when you zoom all the way out, you realize where almost all of this energy really comes from. The convection that drives our ocean currents, the energy that creates our weather, even the energy stored in the food we eat. You can trace pretty much all of it back to the radiation from one giant nuclear reactor in the sky, our sun.
And this quote really says it all. The sun's radiation is the ultimate engine that drives the incredibly complex and dynamic systems of our planet. It is, for all intents and purposes, the source of all the warmth and energy that makes life here even possible.
So from the tiny jiggle of a single atom to the incredible power of the sun, the rules of heat are just woven into the very fabric of our universe. They determine how we cook our food, how we stay warm, how we power our world. And now that you know the rules, the only question left is, what will you build with that?